This is definitely one of my favorite ever step questions, if not my favorite. Just the fact that we're doing some expansion, some division, some integration, we end up with this phenomenal result. This is what it's all about. So first up, let's deal with the expansion. 1 minus x to the 4. Now, of course, you could write this as 4 brackets. We could even just do 1 minus x squared and then times it by itself, so you don't have too many expansions to do. But it's going to be best to just use Pascal's triangle. I mean, you could also do the binomial coefficients, but Pascal's triangle gives you these. So it's going to be 1, 4, 6, 4, 1 as the coefficients in our expansion. So 1 to the 4 plus 1 plus 4 times 1 to the 3 times minus x plus 6 times 1 squared times minus x squared plus 4 times 1 times minus x cubed plus 1 for 0 times times minus x to the 4. That's going to be it. Simplify it. 1 minus 4x plus 6x squared minus 4x cubed plus x to the 4. And therefore, x to the 4, 1 minus x to the 4, is going to be, let me write it in reverse order now. So it's going to be x to the 8 minus 4x to the 7 plus 6x to the 6 minus 4x to the 5 plus x to the 4. Now we need to get it into brackets. We're not actually factorizing it fully because there's this plus b. You might be able to kind of do that, by thinking, okay, a to the 6, that must be just 1 because that's the only way we're going to get x to the 8. You can kind of work logically like that. But I honestly just think, let's go and do a bit of polynomial division. Let's divide the thing that we've just found by x squared plus 1, because then we'll be left with a quotient and a remainder from which we can construct our answer. So here it goes. Just got to do it carefully, but it will work out. X squared plus 1 divided into this thing that I've just found. And then I'm gonna, do you know what? I need to have a bit of space to carry it on. With like smaller terms. So I'll write plus 0x to the 3. Oh, I still can't fit it in. Okay, 1 second. Plus 0x squared plus 0x plus 0. There we go. Right, here goes then. X squared into x to the 8 goes x to the 6. Multiply back through. And do get involved and try this out yourself. Just be really careful with the place value. Okay, minus 4x to the 7 plus 5x to the 6. Oh, wait, it's here. Minus 4x to the 5. Okay, I need to also bring this one down. Then these will cancel. I'll be left with 5x to the 6. These also cancel. Then it'll be plus 5x to the 4. Turns back through. This becomes minus 4x to the 4. Okay, and then actually all the rest are zeros now. X squared into minus 4x to the 4 is going to go minus 4x squared. So we miss out the x cubed term. Multiply back through. And then I'm going to get a plus 4. From which I'll be left with minus 4 as my remainder. So what that means is that x to the 4 times 1 minus x to the 4 is going to equal, let me actually, right, if I divide it by x squared plus 1, I'm sorry, I'm going to take this slow just to make it clear. Then what do I get? I get this quotient that we had at the top, x to the 6 and I've still got my minus 4 divided by x squared plus 1. Okay, because that's my remainder. I've not actually divided it by x squared plus 1. And therefore, if we times through by x squared plus 1, we get this in the bracket. Minus 4. And that's what we're asked for. Sorry, I didn't quite write it as they've got it. I put the x squared plus 1 first, but all the rest is absolutely fine. That b is minus 4, and then I've got all my coefficients of the terms, some of which are 0. Hence or otherwise, prove that this is true. Okay, we definitely want to use the hence here rather than trying to do this integral using another method. So our integral from 0 to 1, this actually, I want it back now as I kind of did it when I did my division. It's going to become the integral from 1 to 0 of our quotient when we did the division. And then I've got this extra minus 4 over x squared plus 1. That's where the pi is going to come in, if you're wondering. You can't see it straight away. We'll talk about that in a minute though. So let's deal with the first, like, kind of, I'll separate into two integrals really. So over here, just got to be careful, but we kind of expect to get 22 over 7. And at least we're only substituting in 0 and 1. Sorry, that should be 4 over 6. What am I doing? Now, this is actually one to note. I don't actually know if at the time this was given in the formula book for step, but the integral of 1 over 1 plus x squared is actually inverse tan plus c. So I will talk about where that comes from in a bit. I just want to kind of crack on with the question. So here we're going to get 4 inverse tan of x evaluated between 1 and 0. I'm actually not far off. So now I can just substitute 1 in to give me 1/7 minus 2/3 plus 1 minus 4/3 plus 4. And then when I put 0 in, I just get 0. And then minus 4 inverse tan of 1 minus 4 inverse tan of 0. This one just disappears. Inverse tan of 1 is pi over 4. There's our pi. So over here I get 1/7. Minus 2/3 minus 4/3 is minus 6 over 3, or minus 2. I got it's 4 times pi over 4, so that's where my pi comes from. And then I'll have 3, and 3 plus 1 over 7 minus pi, which is precisely 21 over 7, so 22 over 7 overall minus pi. And there we have it. Now, just before we move on, let's look at that result and where it comes from. I would strongly recommend learning it. It's also important to know how you actually derive it. In fact, the origins for the substitution I'm about to do come from differentiating inverse tan, which I nearly went through. I just didn't want to get too kind of carried away on a detour. So we let x equal tan u. And when people first see this, they often think, how would you know to do that? But it comes from being aware of the derivative of inverse tan and how you achieve that. And also what happens, why the trig identities are working. If you try to do like sine u, it just won't work out, whereas sine u works elsewhere. Because then we get dx by du is sec squared u, either using the quotient rule or just a result to learn again. And then the integral, using the chain rule, becomes 1 plus tan squared u, I'm substituting in for x, and I can replace dx by du du. Sometimes people like to rearrange the dx, but I like to do it like this. And that there is sec squared u. Now sine squared plus cos squared is 1. Divide through by cos squared to give tan squared plus 1 is sec squared, which means that these two are exactly the same and they just cancel out, giving us the integral of 1, integral of 1 with respect to u, which gives u plus c. And then u is actually just equal to inverse tan of x. So that was very quick. That is proof of the result that I used in the question. Right, final bit. We're asked to evaluate this integral and then deduce this amazing inequality. So right at the start of the question, we expanded that. I do not need to expand it again. Where was it? It was up here. Again, it looks fairly complicated, but the limits to 0 and 1, which will make life so much easier. Hey, we're looking to get 1 over 630 or minus 1 over 630. So the lowest common multiple of 9, 2, 7, 3, and 5 is actually just going to be the lowest common multiple. We can just ignore the 3 because 3 goes into 9. And then these are all co-prime. They don't share any common factors. So it's going to be 9 times 7 times 2 times 5. I did it in this order because this is just 10. This is 63. And we get 630. So it's going to be 70 over 630 minus 315 over 630. Maybe after times by 90 over here, so plus 540 over 630. With the 3, it's going to be 310 times 2, so 600 and... Wait, that doesn't make sense. No, sorry, 210. That's better. 420 over 630. And for the 5, it's going to be 126. Okay, a little bit fiddly, but what should I do? I think I'll add them. Add the 70, the 540, and the 126. That's going to give me 610 plus 126, which is 736. And then I'll deal with the minusing ones. So 315 plus 420 is 735. So our final answer is going to be 736 over 630 minus 735 over 630, which is 1 over 630. Question is, how does that actually help us? Well, we need to try and link it back to the other integral. Remember, we showed previously that this here was equal to 22 over 7 minus pi. Okay, now the thing we're dividing by, 1 plus x squared, is going to be greater or equal to 1 for all values of x. So we're going to be dividing this function by something that's bigger than 1. It's going to be smaller for every single value of x. My integrand for a particular value of x here is going to be smaller than my integrand here. Just going to write that down. So x to the 4 over 1 minus x to the 4 is going to be less than and therefore the integral from 0 to 1 of this is going to be less than the integral we just found. So 22 over 7 minus pi is going to be less than 1 over 630. We can rearrange this so that pi is greater than 22 over 7 minus 1 over 630. We've got this first part of the inequality. Now for the second part, we need to show that pi is less than 22 over 7. It's going to come back to this integral over here. Now we already said that this is greater than 1, but check out these two terms. They're going to be greater than 0. X to the 4, 1 minus x to the 4 over 1 plus x squared is going to be greater than 0 for all x. So the integral from 0 to 1 is also going to be greater than 0. It's never going to go below the x-axis. We're going to get a positive area, guaranteed. And that means 22 over 7 minus pi is greater than 0, which means pi will be less than 22 over 7. We are there. So overall, 22 over 7 is going to be great. How is it written? Is going to be greater than Don't know why they're doing it that way around. Don't really like it like that. I'm going to write it my way around. So let's look at the lower limit on the left, upper limit on the right. Okay, amazing. Using A-level methods, we can find out this some bounds for pi. Okay, of course, there's probably easier ways to get bounds for pi, such as drawing a regular polygon inside circles, has got to be said. But it's just pretty nice that we can find it using integration. Um, just to show you out of interest what we actually get. So if you use a calculator to put this in, 22 over 7 is just a well-known approximation for pi, and it gives 3.14287. In fact, that bit is a recurring decimal. So it's not super accurate, to be fair. And then the other one gives 3.1412698, with this bit being a recurring decimal. They're not good at approximation, but they do give us this nice bounds. And yeah, just once again, amazing question, and I hope you enjoyed it as well.